Okay, so inverse, opposite, undoing, right? Doing the exact opposite to a given thing, or undoing it and getting back to where we started. So dividing by -3. Sorry. If I take some number and divide by -3, then what do I have to do to sort of undo that or get back to where I started? Multiply by, yep. Just to make sure, everybody's on the same page with what I mean, somebody give me a number, preferably that's divisible by 3. 30. 30 divided by -3 is -10 times -3 is 30, right? That's what we're trying to do. Do one, then do the other immediately, which is composition, right? And then end up back where we started. Okay, putting on her jacket, taking off the jacket. If I do one of those and then do the other one immediately after, I end up back where I started, right? If I, as I am right now, put on a jacket and then took off the jacket, I would again be unjacketed, right? Okay, good. What if there are two things happening? Putting on socks and shoes.
You're going to do the latest one first.
The latest one first, right? So what would, how would we like reverse that process?
Take off the shoes first, and then the socks.
Taking off shoes, then, and the then part's important there, right? Then socks. If I start barefoot and put on socks and then put on shoes, to get back to being barefoot, I need to first take off the shoes and then the sock. I guess unless you don't care about your socks or you have different feet than I do or something, but you have to undo the individual things, but also reverse the order. Multiplying by 3 and then adding 1. Subtract 1, then divide by 3. Okay, that's it. That's what an inverse is. That's how it works. That's all there is to it, really. Except that sometimes it's hard to sort of pick out like the individual things and put them in order like that, right? So look at like flip over to the back and look at the very last problem or something where there's more going on. I have a harder time with that. You can still do it, but it's harder to track down like, okay, I'm going to take an X, I'm going to do this and this and this. So to undo it, I need to do the opposite of this and then that and then the first thing, right? That gets a little bit more complicated with a more involved function. Of course, there couldn't be more than 2 things, right? But the idea is always the same. So like think about how you got to campus this morning. I drove from my house and I parked and then I walked up to my office and then I walked into class, right? So to get home, I have to walk to my office because I left my stuff there and then walk back to my car and then drive home, right? I have to reverse the steps, but also reverse the order. Okay. Of course, most of the stuff that we're going to, look at is going to be, mathier, right? Like that last one. So if we talk about the original thing, right? The thing I gave you, the printed part, multiplying a number by 3, then adding 1. If I wanted to write that as a function, I could do it like this, right? You give that an X value, what happens first? If you plug something into that, you multiply by 3, and then you add 1 because the order of operation says multiplication, then addition, right? Okay, take a couple of minutes and think about, or talk about with people around you, how you would write a function that does the thing that we came up as the opposite or the inverse. Subtract 1, then divide by 3. Okay, so what's wrong? Well, not wrong, but what's tricky here? If we want to take a number that we give it, right, so an x, and first subtract 1 and then divide by 3. Yeah, subtraction and division don't normally happen in that order, right? Normally division would be before subtraction. I want subtraction to happen first. The way we force order to happen is to group things somehow, right? Use parentheses or something. So I want, take a value, right? Take an x, subtract 1, then I want to divide by 3. So group that somehow. How'd y'all write this? Do it? Over 3? Yeah. That'd be the usual thing, right? You could write x minus 1 divided by 3. I don't like that division symbol for some reasons. You could write it as 1/3 times x minus 1. Most often, you're probably going to see it like this, though, written over 3. When you write it over 3 like that, the 3's only got 2. I don't know why I'm writing over my 3 anyway. Okay. When you write things like a fraction like that, you treat them like they're grouped anyway. So you can write those parentheses if you want. They're not strictly necessary, though, right? Okay. Okay, good. That's going to be x minus 1 first, and then divide by 3. Let's name that G, just so we can keep talking about it without having to write the whole thing out. Okay, now our sort of claim, I guess, is that this and this are inverses to each other, right? That they're a pair and one does something and the other one undoes that thing. And if you do one and then the other, you get back to where you started, right? Just like, driving to campus and then driving home, right? They're opposite things happening in reverse order. Let's see what that looks like if we look at them graphically. These are both straight lines, so you could graph them, but let's just go the quick way. That's y equals 3x plus, y equals 3x plus 1 right there. That's x minus 1 over 3. And then I also asked you there to graph the line y equals x, but as a dotted line. Y equals x is just the sort of main, like 45-degree diagonal, right up the middle. Okay, so there they are. I've got one line that's got slope 3 and y-intercept 1. So the red one, the original, is kind of steep. The blue one, the slope's 1/3. So it's kind of less steep. It's y-intercept down here, negative 1/3. And then again, y equals x, right through the origin and up and to the right. So there they are. And now I'm going to ask a hard question. What do you notice?
It all reflects over the y equals x.
Ooh, I like it. What does that mean?
That is, it means that it's an inverse of itself. So basically you have a y equals x dotted line and the top one, the y equals 3x plus 1. It intersects at, what is that number up there? It's a 1, right? And then it intersects at 0, 1.
Okay.
And
Okay,
then
sorry.
you have,
I'm looking at a different point.
it intersects the y-axis at 0, 1.
Okay, let's just pause that for a second. Let's back up to the reflection idea. So I had you put y equals x on here for seemingly kind of no reason, right? But what does it mean to reflect about a line?
It's like a mirror.
Yeah, like mirroring or flipping the thing, right? Okay, so you've drawn it on your paper now, right? If you hold that up and try to hold, where that y equals x is still and flip it over and kind of look at it through the back, one line ends up where the other line was, right? And you can also think of it if you fold over y equals x, then one of them lines up with the other one. It's a reflection, right? We've done y-axis reflections. We've done origin reflections. This is a reflection about y equals x. What that means, so let me write that down. Reflection about the line y equals x, it acts like the middle, right? And they're mirror images across that line. They all intersect at one point, right? And that one point where they intersect is -1/2, comma, -1/2. What might be special about that? I think this gets to what you were saying, Sailor, about the coordinates. Let's look at some other points.
So
Let me just highlight a whole bunch of stuff here.
what happens is, so the y-intercept for the y equals 3x plus 1
Uh-huh.
is at 0, 1.
Yep.
And then the x-intercept for
The other one.
the other one
Yeah.
is 1, 0.
Everybody catch that? The y-intercept for one of them is 0, 1. The x-intercept for the other one is 1, 0. So 0, 1, 1, 0, right? So we swap the coordinates. The x-intercept for this one, right? Not as pretty, it's -1/3, comma 0, but the x-intercept for this one and the y-intercept for the other one, swap the coordinates, right? Is it just the intercepts? There's all the other points too. I mean, if you look at what's going on, there aren't, a lot of other like really, nice round points I have highlighted here, but if you look at all the other points, the stuff up here looks like the mirror image of the stuff down here, right? That's the reflection thing, right? So the intercepts for one are the opposite intercept for the other. And the one place where they intersect, -1/2, comma, -1/2, I don't care that it's a half. What happens if you take the x and y there and switch them? They're the same. That's why it falls on the line y equals x. Y equals x means x and y are the same. So all the points, the intercepts, everything, the x and y coordinates swap. If you know a point on one of them, then you know a point on the other, and you get it by just flipping the coordinates around. Well, that makes sense because think about what the inverse is supposed to do. A function takes an x and pairs it with a y that goes with it, right? Its inverse is supposed to do what? The opposite, reverse that. Well, of course, then it swaps the x and y coordinates. X is in, y is out. So the inverse should do those the other way around. Okay, cool. And this symmetry about y equals x, that's always going to happen for inverse functions. Okay, cool. That extends to everything, right? It's all of the points. So all of the x values on this blue line would give you all of the y values on the red one. That means that if you know the domain of one, then you know the range of the other, and vice versa, right? So the domain of a function would be the range of its inverse, and vice versa. So that's cool. That means if we know stuff about the one function, we kind of get everything about the inverse for free, right? Okay. Now let's just test this out a little bit more using some of the new skills that we have now. So I've got these same two functions. F is 3x plus 1, g is x minus 1 over 3. We think they're inverses. We're pretty sure because of what we've seen so far, but let's see what that looks like algebraically. If I plug 7 into g, what do you get? Two. 7 minus 1 over 3. Okay, so we did this. And then I said, now take the result. So take 2 and plug it into the first function, right? So find f of 2. What's f of 2? 7. Does that matter? Do I care that it's 7? What just happened? We got the same thing. The same thing is what? That's the part I care about. don't really care so much that it's 7. I care that it's the same thing as this. What did we just do? We did one function. We let it do its thing. Then we took the sort of result I got in the middle, right? The pile of wet laundry, if you want to use that analogy, and plugged it into the other function. And I got back to where I started. We just did composition. We didn't write it as composition, but this is just f of g of 7, right? That's what we just did. We composed one with the other, and we ended up back where we started. So have we, like, is this definitive? Like, we know now for sure these things are inverses? We've got a whole bunch of like evidence stacking up, right? We found it in the first place by reversing steps in order. We graphed and looked at the symmetry. Now I've plugged in a point. I don't necessarily know, though, that just because it works for 7, that doesn't mean it works for 19, right? So how could we be a little bit more definitive? Well, what if I do that same thing, only instead of using 7, so that I'm sure it's not just something that happened once, I use just some arbitrary symbol, right? What's g of f of x? That's g of f. What's f, though? F was the original one? Yeah, 3x plus 1. What's it look like when you plug that into g? G of anything looks like this, right? Thing you're plugging in -1 all over 3. So
3x plus 1, and then it's going to be 3x plus 1 in parentheses -1 divided by 3.
yep. And those parentheses aren't really doing anything, right?
It's just separating.
It's just separating. So if I drop those, then what happens?
You get 3x plus 1 minus 1, which cancels each other out.
And we get
3x divided by 3, divide 3 from it, and you're left with just x.
yep. Okay. So like, cool, we did the composition, right? We did the algebra to clean things up. What does that actually tell us, though? What does that mean? Does it matter? Did an important thing just happen? An important thing did just happen. What does all that say? No matter what I plugged in, right? This and this are the same.
Yep.
So if I did this with an X or a T or a 7 or a 19 or a half or a little drawing of a dinosaur, one, then the other is going to get me back out exactly what we started with. And that means that they're inverses, right? So for two functions that are inverses, if we compose them, that's always going to be true. All these other things that we saw about the graph, those are true as well. The reflection, the domain and range, the X and Y swapping. The way we write an inverse. Just go to some open space. Is like this. Little -1 superscript. That means F inverse. Or inverse of F. I'll probably mostly say F inverse, but that's just to show that, you know, so I've been calling these things F and G, right? But calling them F and G doesn't really tell me that like they're related to each other. If I talk about F and F inverse, then you know, okay, well, those things have this like special relationship. They're paired together, right? And what we just saw is that the composition, one followed by the other, because that's what composition is, everything always just sort of, you know, it's not canceling exactly, but Everything undoes exactly what happened already. And you end up back at where you started in either order, right? So invert a function and its inverse are a pair. One is the inverse of the other and vice versa. Right? So if I was gonna talk about like the inverse of f inverse, that would just be f. So when this happens, when we have functions that have this, sort of special relationship between them, it does work in both directions. Okay, which takes us to kind of the last question, and that's when does this actually happen? Because it doesn't always happen. How do you test to see if a function is a function? How do we check to see that that is a function?
Vertical line test.
Each x needs to go with just one y, right? So vertical line test tells you if that happens. So here's y equals x squared. This is a function because it passes the vertical line test, right? Okay, when we take the inverse though, and we take all the x's and all the y's and swap their coordinates or reflect it across the line y equals x. What happens when you swap all the coordinates is that you turn the thing sideways, right? So you turn the graph on its side. If I do that here, that would look like that, right? That's what its inverse would look like. What's the problem? That's not a function, right? That doesn't pass a vertical line test. That's why when you undo a square, like if I say x squared is 4, what's x? 2 or -2, right? Because both of those, when you square them, give you 4. Well, you get 2 answers. That's a thing that's not a function, right? A thing that gives you 2 answers like that is not a function. That's what's going on. So the way that we can test for that is with a horizontal line test. If I look at a function and it doesn't pass a horizontal line test, right? So there's a function. That's a function, right? Vertical lines. Does it pass a horizontal line test? No, because right here you hit the graph 3 times. What that means is if I flipped x and y, I would get a thing that looks like this but sideways that would not pass a vertical line test, right? When we talk about a function and its inverse, we want both of them to be functions, right? Look at the top of the thing, right? The header inverse functions. We want them both to be functions. If it doesn't pass a horizontal line test, then it's not called, we call that being one-to-one. It's not one-to-one. If it's not one-to-one, its inverse wouldn't be a function itself. And so like that kind of means we can't do it, right? It's a little bit like when you, well, I mean, like I was talking about here, like this has 2 answers kind of, right? That's what's going on. Okay. So 2.6 homework, you should for sure like knock all that out. Monday's kind of a like open day in the schedule. We don't have new stuff to talk about. So that means we've got